before going into refraction, or having bodies that are translucent or transparent, or having this sphere made of glass so it releases light through and it looks transparent in general, we first gotta tackle the thing that we still haven't tackled since we started this tutorial. I promised I'm gonna cover it, and we need to do it now. We first need to figure out what this dot product actually is, to the core of it, to know what it does, because we used it knowing that we are projecting a vector onto a vector, and we used it to figure out a specific direction of a vector. We used it for determining how bright a part of the sphere would be depending on how big this dot product is between two different rays, and so on and so on. So you know how it works intuitively, kind of. You know how to use it sometimes to determine directions, but you don't know what it does. Maybe you do. If you already learned that and know that, perfect, then you can just skip this part. But for those of you who are not familiar with it and what it does under the HUD, now is the time to watch. So we can define dot product as two different things, in two different ways. The first way is defining it in the algebraic way. So if we have algebraic, that just covers defining it as a matrix and then doing different kinds of math operations to get a number. A dot product in general is also called a scalar product because it gives you only one number. It doesn't give you a vector or anything like that. It gives you just a number that indicates how long a projection of your vector onto another vector is. Kind of. It's the gist of it, but you'll see why it's not exactly like that, because there are some details you need to be careful of if you want to get this number correct. So algebraic speaking, like if we just define them as matrices, you have a vector that looks like this. It's just a vector, contains three numbers. These three numbers indicate the position of your vector, or point, if you will, in your 3D space, which means that this is x, this is y, and this is z, pretty much. If you want to do dot product between two vectors, you have, let's say, this vector, the same one, and you do dot product against another one. So what is, algebra-wise, what is a solution to this if you do this dot, this is a dot product. It looks like multiplication, basically. It's basically this 2 times 5 plus 3 times 4 plus 1 times 2. So it's this times this plus this times this plus this times this. And that's, you get a number here. And that's going to indicate, that's going to be the dot product of these two vectors. Simple as that. However, the thing that interests us more in this sense is the geometrical solution. Geometrically wise, there's got to be something happening in space when we do this. And it does. It really does. So why we use it in ray tracing that much is exactly because it's basically one of two main or major operations you do all the time to nail down the tracing. So let's say we have a unit vector called A. This symbol over here indicates it's a unit vector. A unit vector has length 1, always. We're gonna label normal vectors, like regular vectors, with normal lowercase letters. So we can have another vector called B, and we just name it like this, B, and that's a regular vector that has some magnitude. That's not 1 in this case. Also, the third notation you got to remember, so you have this vector, you have a unit vector, you also have a magnitude or a length of vector that you can indicate, and you indicate this with two lines like this around the symbol, and in this case, the length of this unit vector is 1. So this is how we say, this is the magnitude, and this is the vector I'm indicating the magnitude of. So you got these basics now. If you want to do let's say we have this same unit vector over here. When you do dot product B dot product A, what happens here, you project this vector over here, and this whole thing right now is B dot product A. or actually in this case, yeah, it is this thing as well, but it's actually the length of this vector you see over here. The reason why we're using a unit vector over here, you're just gonna see that in a moment, but basically by definition, this projection or the length of this thing, you get the number over here, is actually the length of projection scaled up by the size of the vector you're projecting onto, which means that if this A wasn't a unit vector, this number or this dot product, to get the length of the projection, you would need to divide this number with the magnitude of this vector over here. Since this vector is 1, so just imagine dividing this product with 1, it's basically the same thing. That's why we're doing it with the unit vector here, just explained it. So this is B dot product A, and since they're going in the same direction, when you're doing a dot product and if they're going in the same direction, you're always going to get a number that's actually higher or larger than 0. If you have, let's say, a vector that looks like this, let's call it C, this is lowercase c, right? That's perpendicular to this axis over here, so it's basically like this. If you project it to this axis, let's imagine that you again have A over here. You get, when you project it, you get something that's of length 0. It's just the point. So let's say if you, in your ray tracer, you want to determine if something is perpendicular to something, it's easy. You just say, well, if dot product is equal to 0, they're obviously perpendicular. So C dot product A is equal to 0. Another important property that you can use to do a lot of things. Just by learning these basic things, you already have the power of doing many things in your ray tracer. And the third scenario is having this D vector that points in a different direction. And let's say, I'm gonna do this. Let's say that you have A again pointing in this direction over here. So if you wanted to project this vector onto this vector over here, you would do the same thing. You go for a perpendicular line and then you project it, so you get something like this. But this line over here, since you would need to do translations and stuff, in short, what happens, you get D times A is less than 0. Maybe I didn't write that really nice, but basically, now rewrite it. So this dot product is gonna be less than 0. So if they're pointing in a different direction, or actually what happens here, you usually, since if you wanna project this one into this one, normally you can't really do it. There is no way to put a line down and project it so it has this right angle. So what you actually do, you do minus A. So you flip this vector over here, this unit vector, and that's why you have this minus. It flips here, project it, and whatever happens here, you're gonna get a number that's negative because you needed to do this flip first. And pretty much, that's just me trying to explain it in a way so you remember why it happens. So you just flip it. You flip the direction by changing the sign. So basically, if you multiply by -1, it flips to the other side. It always flips in the opposite direction. Same would happen in 3 dimensions. It would just, if you multiply all the coordinates with -1, it would just flip to the other side 180 degrees, pretty much. So yeah, that's how it works in the basics, how it works with basic numbers and basic vectors. One important thing and one important property of dot product is it's commutative, which means that if you write A dot product B, it's going to be the same thing as writing B dot product A. You see it from the algebraic solution. It's quite obvious. Like if you flip these two and do the same calculation, it's the same number you get. So you know that. Also, if you try to scale, if you want to scale one vector up, let's say you want to scale A by something like K. K is let's say a constant we scale it up with, it's not gonna matter in the end of the story which one you scale, because this one is gonna be the same thing as writing a times kb. So it's another property you can use and it's quite useful to know when dealing with this, dealing with dot product. Another thing, like usually when you deal with math operations, you have commutativity, but you also have distributivity. So you also have distribution. Can it distribute? What does that mean? Let's say you have a dot product b plus c. So does it distribute? Does this dot product distribute on both? Like, does it work with normal multiplication, basically? So we can easily check that if you just write something like, let's say you have ax, ay, y, and a z, and you want to multiply it with, so b plus c is basically bx plus cx. This is going to be by plus cy, and this is going to be bz plus cz. So if you do this calculation over here, you're going to notice that in the end of the story, you will get that it distributes the same way. So let's just quickly calculate it. So it's bx plus cx plus, we're just doing the regular dot product rules. So by plus cy plus az bz plus cz, right? And then we can write ax bx plus ax cx plus ay by plus ay cy plus az bz plus az cz. And you're gonna quickly notice that you'll notice that what you have here is, let's say, you can notice these. So you can easily write, well, this is ax bx plus ay by. It's basically a dot product between a and b. And then you'll notice these, and it's basically the dot product between a and c. And look at it now. This was the start, and you have this one. So it distributes. That works as well. Dot product is a really nice operation to work with, and it works like a normal multiplication to some extent. You know that now. That's important. Let's go further. So we can. This was distribution done in the algebraic way, and we can do it in the geometric way as well. So we're gonna do this axis again, and we're gonna make this a unit vector again. We're gonna call it a. A is the most popular vector in this tutorial. Nice. Then we have, let's say we have b and c. So we wanna do the same thing as we had before. So we wanna do a dot product b plus c and see if what happens geometrically wise with them. So let's say we have b like this, and let's say we have c like this. I'm drawing them like this because we want to have, usually when like the sum of two vectors is going to be this now. So if you connect them, this is going to be b plus c. I'm not going to explain this because I consider this to be like the basis of vector algebra, that you know that this and this is their sum. If you don't know this, then I definitely advise you to just read up about it, but it's simple. You just connect the start and the end of this one geometry wise, and whatever this line is, that's their sum pretty much. So what happens geometrically wise? If you have this a as the unit vector down here, and you want to do, let's say you want to project this sum over here, the sum over here would look like this, and it would be here. So I can extract it like this. So this vector over here is actually a times b plus c. Right. So geometrically wise, how do we prove that this distributes, right? You can do this projection over here and you get this vector. I can extract it even more. I hope you'll be able to follow this, but yeah, this is A dot product B. So this line over here is A dot product B. And then let's say we project C on this one as well, and C goes from here to here, so C is this vector. So we can extract C as well. A dot product C. Look at this now. We see this one and we see this one. So if you just think about it, you can see that this one equals this one. Cool. So you know that you can prove it both in algebraic way and geometry way, and you also know now how these two things are interconnected, and that's super valuable. However, we still haven't touched the most important part of it, and the part that's crucial for working further with refractions. And that's actually figuring out angles and how does the dot product actually, how is it connected with the angle. So we're gonna quickly explain it, and after I explain this, you'll be ready to go further into math, and you'll be ready to go further into refraction. So let's do it. Let's say we have again, we're gonna do our axis. You can draw with me as well, like try to do this on your own. It will help you remember these things later on. And I'm pretty sure you'll forget this like 15 times before you nail it down. And every time you do it, you'll be like, well, I don't actually remember how this worked, and you'll go back and look into it. But that's normal. Just like try to do this, you'll forget it 10-15 times probably, and then just go back to it and you'll soon figure out how it works again, but much faster than the last time. So let's say you have this unit vector over here, A, and let's say we have a unit vector B, or not the unit, sorry, just the normal vector, right, B, as we had before. B vector, or each vector in 2D space, has two components that make it up. It has X and Y component. As I said before, this something over here is pretty much what we did with that. So B has this component, which is its X component, and we can maybe call it, we're not going to call it X. There is another notation we can use, so we're going to use B this, which is kind of the parallel, and then we have the perpendicular component, which is this one, just for the sake of it, because it's gonna be like, maybe it's gonna be messy to go with X and Y. This is easier to map in your brain. And then there's one important thing, we gotta have this, and this is this angle. So how does a dot product relate to this angle? What's their connection? Like in the refraction, you're gonna need to figure out what the angle is, or how much your array breaks or diffracts depending on the media it goes through. In water, it's going to break more than in air, and so on. So you need to know this. So first, we're going to break this B vector into its parallel and perpendicular component. So we're going to say, well, the parallel part is basically what this vector is. If you do this, you get the length of the projection of B onto this axis. But that's just the length. So it's going to be number 5. It's not a vector. To make it a vector, it's actually easy. You multiply it by this unit vector you have here, A. Why? Because this vector determines direction. What you do here, you just scale this vector up to this point by multiplying by this magnitude over here. And be careful, you can only do this with this unit vector. If this was like, let's say here, and it was a vector A of a specific length, this math wouldn't work. So you need to be sure when you're doing these things that this vector is normalized and its length is 1. You can easily normalize any vector. You just normalize it and then you can work easily with it. So be careful with that. Now we said, well, b is the sum of this and this one. Remember, we did this here. B and C was B plus C. Same thing happens here. This component plus this component makes up this component, which means that we can write this. So how do we figure out what this component is? This component is B minus the parallel component. Cool, we got that. And then we can write, let's see, this one stays the same. What was this? We go back here. It was this. Well, what did we get with this one? Well, we'll see in a moment. Let's just save this formula for a bit. And let's go back to the basics of trigonometry first. What we're gonna do next, I'm just gonna quickly draw another triangle that's gonna be slightly different, but it's gonna have this one major difference. It's gonna have two edges that are actually both unit vectors of length 1. It's like in the last example, our b was not a unit vector. It was just a normal vector, it was a regular vector with regular magnitude. But in this case, it has length 1, the same as a. And this angle theta over here is the thing we're asking questions about. And how does this interact with dot product? And why did we even break these components and so on? Well, it's gonna start falling in place right now. So the first thing you want to do, if you're going to do it in the vector algebra way, you're going to break b into two components. So you're going to make b perpendicular and b parallel as two different vectors, components of this unit vector b. So right now, if you remember, basic trigonometry teaches us one thing. It says that the cosinus of theta is the ratio between the length of the adjacent edge and the hypotenuse, which is the longest edge in the triangle. And this is, of course, a right angle. This is perpendicular to each other. And that makes sense. What is an adjacent edge over here? How do we do that? Well, adjacent is obviously, let's just write it out step by step, is the length of this parallel component of our b unit vector. And hypotenuse is the length of b vector. Well, that's a unit vector right now. And now I'll give you a second to think about how we can simplify this just by looking into this. But you should have figured that, well, this has length 1. So cosinus of theta, because it's a unit vector, right, is actually this. Wow. Next step. What do we do next? What is this component? Well, if you look at our notes and what it did here and why we broke this down, we have this line. So we're gonna write that over here. So I'm just gonna copy and paste it over here. That cosinus theta is gonna be this one. So it's gonna be p times a times a. But there is one important thing that we need to keep in mind. B was, in our example from this one, b was not a unit vector. It was just a regular vector with a magnitude. So what do we do here? Well, this is actually a unit vector. Another thing that we said, so now we're looking into this expression and wondering what we can do next. The important thing to say is that this thing over here, so this perpendicular component, this was the length of it because it's dot product of this vector onto this axis over here. What we said, well, we want to have this vector, not the length. So we multiplied it by this unit vector a. So we basically scaled this up to get a vector, not a number. So what we can do here actually, we know when we're calculating the length, a unit vector is nothing but 1. And we also know that we did this to get a vector and so on. So you can just go back or just convert this into 1, because if you're calculating the length, it's like it's not gonna really do anything. So cosinus theta is gonna be equal to this. Why? Because we said this is a vector. Without this, it's actually the length. It's the dot product that the original projection to this unit vector. And we get this expression over here. It looks simple, right? So let's write it again. Let's write it by having a on the first spot. Like this, it makes more sense. And it basically means that the theta angle is arcus cosinus like this. And now these are unit vectors, right? And we're gonna deal with you can deal with this, like you can have scenarios where you don't normalize it, you want to get the angle directly without normalization, you can do that as well. But then let's just go one step back and write, well, cosinus theta equals, so we go back, we have this expression over here. We said, well, these unit vectors, this expression is same as saying a dot product b, and then you divide it by the length of b times the length of a. Pretty much is the same thing. And this is the expression you can use if you don't want to normalize the vector. So you can write that the theta angle is arcus cosinus of these. However, what you usually do, like it doesn't really make sense to do this, you actually just normalize vectors and then use this formula over here to calculate the angle. That's the way you do it. So this is the golden formula. I'm just going to rewrite it here, caps lock, because it's the one of the most important formulas you're going to be using. And that's pretty much it. Now you know how to calculate this angle. And that's the most important part regarding a refraction, because in refraction the angle is going to depend, or it's going to depend on the refraction index, so-called refraction index of the media it's falling into, and so on. And we're going to be using this formula to elaborate more further. So this lesson was purely mathematical, and you can skip it entirely. You could have skipped it entirely, but I think if you followed through that, you learned something at least. And in the next step, when I start dealing with mathematics behind refraction, it's going to be much easier for you to actually dive into it and figure it out. Unfortunately, if you don't like math, then probably doing rendering is not really something you should be doing, unless... it's not really that straightforward without knowing these basic concepts. It doesn't need to go too deep. You need to know these basics and some more to deal with a lot of things in rendering. Let's take a small break from math and go into coding a bit, and then we can go back into math that's more specific to refractions later on. Before doing anything further, I want to do some refactoring on our code, because right now it's all over the place. We're not gonna do a huge refactoring, just a small tidy up, and it's definitely not gonna be tidy as it should be. But let me do this. Okay, first things first, I noticed that our material is completely independent of the sphere, and I want this sphere that we have, I want the sphere itself as an object to have a material, so we'll just move things around a bit. We're gonna define this material before our sphere, and then in our sphere we can say material, and my keyboard is, yeah, there you go. Then here we can define just this block below. It doesn't need to be below, but we're going to put it so it's together. And I'm going to say that sphere.material equals material. Now let's see where we used this material down there. I'm going to swap it. So we're doing some ray tracing here, sphere color, material dot specular. We're gonna do sphere, material, specular, sphere, sphere, here, here, and we're gonna do it here as well. Okay, it's compiling, that's good. Now let's see what we can do here. We have the reflection, we have fog. Let's not touch this part for now. Quadratic is okay. Yeah, okay. Let's actually dig into the ray trace function. We're gonna change this function quite a bit in the next few tutorials. So let's do it now. I want to have a way of displaying the different kinds of shading per request. So I want to change one argument and then have fog displayed only, or I want to have only reflections shown or reflections with fog and so on. So we're going to quickly just to do this. We're going to say int mode equals 0. Let's set it to 0, and then if we intersect, we're gonna say switch mode. I'm gonna say case 0. Well, if case is 0, let's say we want to have only fog. If case is 1, we want to have reflections, but only reflections, for example. Then we can do case 2. We can say reflections plus fog. Okay, let's see what we're doing now. Okay, so we're still using this directional light. We're gonna cover point light in maybe this one, this tutorial. Maybe we're gonna cover it in the next one, depending on how this goes. But I think this is gonna be quite a long tutorial already. So let's just stick with the directional light for now. So let's just say that this part deals with, this part deals with reflection. This part deals with fog. So we can actually do this. We can do get fog color here. So we can use this function to get the fog component of our ray trace of our sphere. What do we need here? I think we need this coefficient, or we don't. That's good. Ambient sphere. Yeah, for now we only have one sphere, but we could possibly, let me think about it. Do we really need it? No, let's just leave it like this. And then instead of doing this, we can okay, so we have something here. We have light direction, but we also have this direction, which is the ray direction. We can do this. And we don't have the surface normal. And yeah, coefficient I was searching for. I knew that that thing was there. However, we probably don't need, we want to keep the calculation possibly inside of this one. So we only need the light direction. So I'm gonna keep this light direction together with this one. And then here we can do this calculation. And here what we need to pass the direction, which is our view direction, then light direction, and then surface normal. Okay, and of course right now I don't think this makes any difference. Let me see. Okay, we're returning this one. Are we returning anywhere before this? No. Cool, but we are doing this. Yeah, okay. here. So if we did this, then we get this one. So we can move this one here. So if in case this is set to 0, this mode thingy over here, we're gonna get the Phong component only. If we have reflections, we can do this. Since this was our, yeah, so we have the sphere color, reflected color. Okay, let's do this. And we need these as well, for example. And then we can just kill this off now. Act like nothing is happening there. And if we do this now, we get the same behavior because now we are returning this Phong color. I'm just thinking that we should also just extract this to the function. We're gonna do more tidying up in the future. This is not super tidy still. Get reflected color maybe. And let's just, like the way I do it, I just usually paste it in and then see what we are missing when we compile it. Let's see. Yeah, of course, we're not returning the value. And we are mixing in the sphere color. So we can do, instead of setting the sphere color like this, let me think about it. Yeah, we're doing this weird mixture over here. We can return this mixture, for example. Then we have the direction. Surface normal. Cool, and now our sphere color, in this case, like this whole logic is not super perfect, to be frank, but it works for now, so let's just stick with it. Reflected color, direction, surface normal. Cool. Let's see what happens now when we set the mode to 1. We get nothing. We get nothing because we don't return anything right now. So our sphere color will be this one. We don't need that. We can return this directly. And there we go. We get the reflection. There is no light on this reflection right now. If I move it, nothing happens. And that's why I left this third case over here where we could combine them. And the way we combine them, we can just get the color, the base color, which is going to be the reflected color, and then we apply shading on top of it. Usually when you're doing these kinds of things, these things go in several passes, and you can just split them in a separate pass. So the lightning shading or whatnot goes after getting the original color and so on. But yeah, that's not the intention of this tutorial. It's just learning the basics of ray tracing, so I'm not going to go there right now. And then when we get the reflected color, now we can just save it temporarily like this. I call it final color because here we are doing some blending between colors. We have Phong shading and we have this reflected color. So what we can do final color this, and then we can try getting the Phong color component. And what we did before, let me remember, yes, so we used, inside of this Phong color, there is this sphere color that we are using directly from the sphere object. So if I'm calling it from here and I have a color that's obviously a different color than the original sphere color, I would need to pass this final color here to kind of get this blending happening. So how would we do that? Well, we can just do it like this. Object color. Here I'm already aiming towards something we should strive towards, which is having these functions completely agnostic of any kinds of objects, so they don't persist any state. They just get something on the input, like a bunch of vectors, colors, and they output the color in this case. They should work like that, and it's not the case right now, not even close. I mean, we could actually, instead of doing this, we can pass, since we only have one type of object now, we can pass sphere like this, so we can control what kind of sphere. If we have more, you can send another sphere here, but we don't have it right now. Just send the color, because that's the only thing we're dealing with right now. And then we can replace these colors. Yeah. So right now, I mean, the same thing happens with reflected color, but it's not important in this context because it's the first calculation we do here, and it just returns the, it does the calculation with the original one. It's the first one, so we don't care at all. So here we're gonna do, or actually, let's call this reflected color because it's actually not the final one. And then let's use this reflected color here. And the color we get with this Phong calculation should be the thing we want to. Let's try to compile it. Yes, of course, we need to pass the color here, and we can just use the original sphere color. Cool, and this works fine. But if I do this, then it changes. So you can see that now we have reflections with Phong. So just imagine if you did this, you can keep changing just this number to see how different. Of course, when I typed 3, nothing happened because we don't have a case for it. But you can quickly change how different components of your ray tracing work. Like if you want to see only outlines of objects, you can have a separate logic for calculating that, and it's useful. You can even have them running in parallel, like split the screen and you see half of it in one style and half of it in the other style. It's useful for debugging purposes. If you want to color a certain part of an object depending on the angle of the ray that goes into it and so on, you can color it red. If it's less than this angle, you can color it blue, and then you render that on screen. You see a pretty good debugging view of what you wanted to do. But it's quite cool. You can play with these kinds of things as much as you want. The thing we want to dive into right now, actually, and this is it sounds like a simple subject, but it's really not simple. You can if you're really good with it, you can nail it so much that it looks super realistic. If you just do the basics, it just looks like a special sphere. It doesn't look as realistic as it should. The thing we're gonna be doing right now in this first part, because if I went deeper now, we would never finish this tutorial. It's just gonna be this basic translucent sphere. It's gonna be a sphere that's gonna be made of glass in this case, and we're gonna see how it behaves and how it interacts with light and the environment behind. I mean, you already know how a glass sphere works, but now we're gonna see how the math behind it actually works. So yeah, let's I think, let me see if we have anything more to do here. No, not really. This code is not, it's 176 lines of code for rendering a sphere that is fully lit and it's the reflecting environment around it. I would say that's pretty okay. And you should be proud of yourself so far if you manage to figure out what's happening here. So let's start with the second part of this tutorial. That's gonna be the harder part. Let's dive into refraction. Okay, now is the time to dive into an important part of the math part of this tutorial, and that's covering refraction. So what is refraction? Let's say we have this. Let's say we have air on this side, and then we have water on this side. And let's say we have a ray of light that comes in this way. We can indicate this ray with I. Then we have the surface normal that goes like this. We can label it as N. And then we have the reflected light ray that goes this way, which is R. And it's the same, the angle between R and N and IN is the same, and we label it as theta, the same angle. And this is reflection. So that's the thing we covered in the last tutorial. Last time when we did reflections, we used the built-in GLSL function to calculate it. This time we won't do that. We want to see what's happening under the hood, because I think it will be quite useful for you guys. So if you do this, this is the normal in the opposite direction. What happens with a refraction is that instead of the light going the opposite or bouncing back completely, some light actually goes through it and bends a bit. Why does it bend? So the law of physics tells us if a ray of light goes from one media to another that has different density or structure in general, the light is going to change direction. And it's going to change direction in a way so it follows certain physical rules. We're just seeing a second one of the rules we can apply to calculate this. But it's going to bend, and we can, by the way, we can label this one with T. It bends. And the simplest example of this that you can think of, if you put something in a glass if you have a glass of water and you put a pen inside of it, you'll see that pen being broken in all sorts of ways, and that's refraction being shown in a real life example. You see that all around. In the case of sphere, what happens there is you usually see when you take a glass sphere, you see the world upside down, because what happens in sphere, let's say we have this sphere over here, a ray can go in like this, and let's say this is a glass sphere, of course. This is the normal, surface normal. This light is gonna bend like this. Maybe not this much, but it's gonna bend. And then when going out, it's again going from air to glass to air, it's gonna bend again. So what happens here, when you hit ray tracer, when you hit the sphere on this point, you're gonna see something that's here. And same happens from this side. If you go like this, it's gonna go like this and like this. And guess what? It goes the opposite. So you're gonna see the world upside down. And in our case, that's gonna be the case. We're gonna be using our sphere and refracting to it. It's gonna look the opposite. The world is gonna look the opposite. Okay, so that's like the basics. But how much does this light actually bend? How do we calculate that? Before going into it, there is a thing called a refraction index, or index of refraction, also called IOR. It's spelled like this. You can remember this. You might see that around. Each media has a specific index of refraction, and it's labeled with eta. It's a Greek letter eta. So we're going to say eta 1 and eta 2. It's spelled eta. So each of these two has a specific index that defines how much this is going to bend. In general, refraction index eta is equal to the ratio between the speed of the light in vacuum, which is labeled with C, you probably know that already from physics classes, and V, which is the speed of light in this specific media. So if we are talking about N2, for example, we would have eta 2 it would be C divided by V2, which is the speed of the light in this media, in water. So it's the ratio between these two. And if you look it up on the internet, there's been a lot of physical experiments already, and we know what the speed of light in water and other major media is already. So for water, it's usually the index ends up being at 1.4 if I'm not mistaken. Let me just quickly check that. I think I can find that online. Yeah, the water is actually not 1.4, it's 1.3. You also have glass. Glass is 1.5, and we'll be using this one. And then you have diamond material, for example, that's 1.8, and so on. Each material can have, or it has, a different refraction index eta. Okay, so now you know the basics, but you still have no idea how you're gonna get this theta 2 from theta 1. You have no idea how much this is gonna bend based on this index. Like, you still don't have that information. So for that, we're gonna be using a law called Snell law. You can look it up. It's spelled like S-N-E-L-L. And that law says that the sinuses, or the ratio between sinuses of theta 2, theta 1, is equal to the ratio of eta 1 divided by eta 2, like this. And that means that if you want to find out what this is, you would do this. You would do sinus theta 2 equals sinus theta 1, like this. Cool. So you know that. You can now go in your ray tracer and calculate this. However, this still doesn't give you enough information. You need to get this vector, not the angle only. You need to know the vector to know which thing you're going to be hitting. So you need to know what this vector over here is to be able to hit something behind. Also, for this tutorial, we're going to kind of ignore what's happening here. We're just going to go straight from this point. It's simpler, and we can cover this scenario later on, because we'll need to change our code quite a bit to make it work. But it's still gonna look realistic enough for you in this tutorial. Okay, let's see where to start. How do we get this thing over here? Well, we can cheat the system by doing a simple check that was done to calculate this a long time ago. We can use a unit circle, place our vectors in that unit circle, and start filling with it so we get the right numbers. You can draw it like this. And we're going to say this is cosinus, this is sinus, x, y. Cool. What does a unit circle mean? A unit circle means that at any point on this circle, if you spawn the vector towards it, the length of that vector would be 1, which means that that vector would be a normalized vector. And that's important in our calculations, and you'll see in just a moment. So the vectors that are important here are the incident vector, or the vector that goes in like this. Then we have the theta angle, theta 1, that's here. And then we have the vector that we get by a refraction that has a certain angle here. And we're going to label it as t. And now the whole idea is, well, try to use this circle, unit circle and vector algebra to calculate this vector. So the way you do it, it's pretty much like this. We need to split this t into two components, the parallel and the perpendicular component. The same thing we did with dot product earlier in this tutorial. So what you do, you basically take this component. So this is called, in this case, we can name it B. And then we take this one and we name it A. So this is A, this is B, and T equals A plus B. Okay, fine. That's D. Cool, we're done. Not really. We need to know what A is and what B is. We still have no clue what they are. So we're gonna do some trigonometry tricks and some vector tricks to make to actually get them. So B is actually pretty easy to get to, because if you look at how where it's located and so on, you can easily realize, since this is cosinus axis, by following trigonometry rules, you should know that B is cosinus of this angle over here. So basically this vector projected here, but multiplied by minus n, which is this one, and this is, of course, as we said before, this is n. So if you do cosinus of this angle, you get the yeah, you get the length of this thing, but to get the direction or to get the vector, you need to multiply it by a vector that goes in the same direction. So you kind of do this. You say cosinus theta 2 times minus n. So you get the value of it, and then you multiply it by minus n, which is also, it's a normalized vector because it's in the unit circle. So you get this b. You get the correct length of it in the correct direction. So that's kind of, it's like a hacky math way to do stuff, doing it like this. So I really like this. Let's go further. A is lying on the sinus axis of this one, which means if you take this angle and do a sinus of it, you should be getting length of this thing. So you have sinus theta 2. A also lies here. So it doesn't really matter where you place it. Sinus of this angle is going to give you this, because this angle over here is the same angle. Just so you don't get confused. So what do you do with this length? Can you see any form of vector here that might help you point A or this whole magnitude towards a certain direction? Well, there is a thing that we need to add here, and we can add it. We can add this vector, and we can call it m. So m goes from here to here, is this unit vector. And it's a unit vector again, because this is a unit circle. I'm gonna do this. Okay, so we can just multiply this by m, which means that, oh, we have the magnitude, we just need to point it in the right direction, which is a unit vector. And if you multiply it by this length, we get a. Simple as that. However, there's a catch. What's m? We have no idea what m is. So we need to find out what m is first to be able to know what a is. So we know b, and a is this times m, and m is question mark. So the smart way of actually figuring out what m is we need to do some more steps around here and add more vectors to actually make it happen. So the first thing you can do, we can project this I vector onto this axis, and we can call this vector c. And that c is gonna be what? Let's see. Well, we have n. So what is this? N times I. How do we do this? Well, c is basically, if you take this angle, the same we did with this b over here, you take cosinus of this, poof, you basically take the magnitude of this cosinus, which is going to be the magnitude of this one, and you need to point it in the right direction, which is going to be what? It's going to be n, right? So you know the length of it, and then you point it in the n direction. So you go with cosinus theta 1 times direction n, because it's this one. So you get c. Cool. Why do we need this c thing? Well, see in just a moment. C is going to help us calculate m, because what happens here, if you do I plus c, you get a vector that's this one, because we said that the sum of vectors, so this plus this will give you this one, and so this one is I plus c. What happens here? Well, with I plus c, you basically know the direction of m, because it's perpendicular to m. You know that because, sorry, not perpendicular, parallel to m. You know this because this is perpendicular to n, because we managed to get to it. If you're a bit confused by this, just go through it a few times and you'll soon figure out why this is so. It's not that hard as it might seem at first. But this is all pretty good if you want to dig into it, just follow through. It's interesting. So you have m. M is I plus c. This is I plus c. But how do we get m? Well, we just need to we need to know the length of this I plus c and divide this thing, the length, with the length itself, or because what happens there, this is I plus c is a vector. If we divide it by his own length, we get a unit vector. It's gonna be 1 of length 1. And what is the length of this one? So this is sinus axis. You have this angle over here. So what you do sinus theta 1 and you get the length of this. Do you get it? I hope you got this. So I plus c divided by sinus theta 1 is gonna give you m. Because in the end, it's gonna be, you're gonna get this vector over here, I plus c, and divided by its own length, which is gonna jump to basically n, pretty much. Okay, cool. So let's keep on moving. Buckle up. There is, so now a, we go back to a, and we said that a is sinus theta 2 times m. And now we can, instead of writing m, we can write I plus c divided by sinus theta 1. And b is minus cosine. I'm just copying this because we already had this calculation. Okay, a and b are there. That's good. And t was a plus b. That means that t is sinus theta 2 times I plus c divided by sinus theta 1. And minus cosinus theta 2 m. Nice. We're gonna move a bit to the left so we have more space. Maybe I can even start here. So we got this formula now, and we still have no clue what to do with it. So we're gonna try tidying it up to see if we can get a form that makes some sense. So first things first, you'll notice, let's rewrite this in a better way so it's more obvious what's happening. T equals sinus theta 2 times I plus c divided by sinus theta 1. I'm just writing this thing in a neater way. Minus cosinus theta 2n. And you'll notice one thing that I mentioned before, and let me go back to that. Do you remember this Snell law that we mentioned? We can finally actually do something with it. It says that this ratio between theta 1 and theta 2 is equal to this thing. So if you go back here, you'll notice that we have this same ratio over here. So let's try substituting this and seeing what we get with substituting with the eta factors. So let's see. Eta. Okay, so it's the opposite, right? So we're gonna do eta 1 divided by eta 2 multiplied by I plus c minus cosinus theta 2n. That's the thing we currently have. Okay, it looks better. It looks better. Let's see what else we can do. I plus c. C is what? Yeah, C is exactly. C can be interpreted as. Okay, let's try swapping this, and I'm also thinking if we can swap more. Okay, let's do this. I plus C. If you go back here, C is actually, we said before, C is cosinus theta 1 times n. So let's try actually replacing the C with that. Cosinus theta 1 times n. Cool. And then minus cosinus theta 2n. Oof, it's getting messy. Let's see if we can do more stuff here, if we can clean it up more. Okay, this angle is problematic, of course, because this is the angle we really don't know, right? So we want to get rid of this theta 2 thingy. So let's try focusing on that one first. So I'm gonna write a bit lower here. T is gonna be equal to, let me see. Okay, this is gonna stay the same. Eta 1, eta 2, I plus cosinus theta 1, n. Okay, and then let's try doing magic with this one. First, the trigonometry identities teach us that, let's write it here. Cosinus of an angle, we can name it theta, is equal to square root of 1 minus sinus theta squared. That's the trigonometry over there. It's basic, and I'm not going to be explaining this one. But let's just use this knowledge that you should have gotten in high school and just put it here. Put it here, or actually not here. Put it here, and try to see if we can get more out of this expression. So if we do this, we do minus. So we're replacing this cosinus 1 minus sinus this one, multiplying it by n. So we still have no idea what's happening here, and we still have no idea what we can get from it. So let's see. And this is of course theta 2 again. Okay, what we can do here, we can do. Did I possibly miss something? Oh yeah, the next thing we can do here, we need to get rid of this, so we use Snell law again, so we can do this. So this stays the same, but we do this. So we said sinus of this angle is equal to, where did I write it? Did I write it here? No, it's on the other side. So the sinus of an angle is sinus of the other angle, and then you have this expression. So we need to copy and paste this expression instead of this one there. So we can do that right now. So we're going to say that it's actually that we have sinus 1, and let's see how the ratio went. Yeah, we have eta 1 and eta 2 like this. And that's squared, and then times n. Oosh, okay, it's going somewhere. But what we'll need to do next, we're gonna need to do some substitution, and that out of that substitution, we're gonna get different parts of this equation that are gonna be easier to solve, or actually, they're gonna be easier to map to our code to get the diffraction or reflection, working. So the first thing, we're gonna replace these etas. We're gonna replace them with only one eta. It's gonna be eta equals eta 1 divided by eta 2. That's going to be the first replacement. The second replacement, we can replace this cosinus theta 1. Cosinus theta 1, we can replace it with n dot product I. And why we can replace this with n product n dot product I, it's because of the thing we did in the first part of the math in this tutorial, where we said that the cosinus of this angle is actually the dot product between these two. So we know that now. We're not going to go into it. So we're going to just write C1. We can name that substitution C1. And we can say that cosinus, that it's equal to cosinus theta 1. And that's equal to n dot product I. So we're going to try to shove this in here. And we have C2. C2, we can basically say that C2 is this this whole expression under the square root. So we can say that that's or not under, but the whole thing. It's actually this. Since we already replaced this, we can use that replacement immediately. Okay. And now if we try to write it out in its final form, it's going to be something like t equals eta times, let me see if we replaced anything here. Yes, so we have I plus C1 is cosinus this, or C1 is n times I, but for now let's do n times I times n. Okay, I plus, okay, just checking if I did something stupid, minus C2n. So we just replaced all of this with C2 and now it's C2n. We could have used actually C1 here and then, yeah, I should have done that, sorry. So we do eta I plus C1n minus C2n. And now you have the formula, and I'm gonna put this formula on the screen while we do the code so you can map it to it. There's also another format that we can use that might be a bit neater or simpler to use, which is if we multiply all of these, we're gonna get slightly different term here. So we're gonna do this. And we can use this expression over here as our main expression through our diffraction coding. Whoosh. Okay, so this was a bit long. But yeah, if you follow through it, then good job. At least you know how it works under the HUD. I mean, you know exactly how diffraction works now. And it's actually not that complicated math that brought you here. You know exactly how a certain ray of light might refract and so on. So let's dive into code now. Okay, the math part is finally done. Now we can start programming. The thing we're going to do now, we're just going to take the formula. I'm going to put the formula in the video so you can see it and have it available during the course of the programming part of this. So we're going to take that formula and basically paste it to GLSL and make our sphere transparent, or like a glassy sphere, pretty much. So we want to do what we want to do. We want to add another case. This case is going to be called refraction. And here we want to do our refraction calculations. For that, we're going to make a new function called get refracted ray. And we're going to try to get our refracted ray over here. There are several things that we need to know. I'm just looking at the formula right now. So we have this eta thing. We have C1, we have C2, and N and I we already know. And we got to get this T thing out of this this function. So let's go step by step. What is eta in this case? I'm going to call float eta equals, what is it? We don't know. So we're going to do float eta equals eta 1 divided by eta 2, right? That's what the formula says. Here we're going to say that eta 1, it's the first media that the ray comes from. That means that in this case, eta 1 is going to be air, which is 1. Eta 2 is going to be the media where the light enters. In this case, it's going to be glass, so it's 1.3. I think glass was 1.3. Let me quickly check. I think glass was 1.3. We can easily fix that later on. It's not a problem. So when we do this, then this eta thing is by our formula, eta 1 divided by eta 2, and we do that calculation there. Float C1 is cosinus of theta 1, or dot product between n and y, I according to our formula. So we can do dot and I. And I are vectors that we're gonna pull them from somewhere else. So we can do this. Cool. C2, it's float C2 is a bit more complicated. So we can do C2 is SQRT 1 minus eta times eta. It's eta squared pretty much. And then we have sinus of theta 1 squared. Sinus of theta 1 squared, we can get that from the trigonometry identity that says that sinus theta is 1 minus cosinus theta, and that's 1 minus n times I squared. It should be. But we can also, just for the sake of it, we can also do a we can calculate theta maybe. And theta in this case is gonna be arcus cosinus, if you remember the first math part we did, of dot product between n and I, which is C1. So you can leave it like this. And then our theta is sinus of theta times sinus of theta. Oh. Okay, that's C2. So we have C1, we have C2, and we're ready to go, I think, right? So T equals eta times I plus n times, and then we do the parentheses part. So it's going to be eta times C1 minus C2. And then we can return that to T. Okay, so this expression, if we didn't do any mistakes, and we might have done it, we can easily fix it, should return a refracted ray from our sphere. There's one thing I gotta explain before we proceed further. I promise this is gonna be super short. So I said one thing when I was explaining what we're gonna be doing here, and I said, well, we're gonna have this ray. Let's just take another color, possibly this one. Yeah. So if we take this ray here, it hits the sphere like this, and then you have this normal going out like this, right? And we said, well, it's gonna move a bit. It's gonna bend, right? Because it's entering a body that's of different density. It's a different material basically, so it bends. And then I said one thing that's not entirely correct, that I just said it for the sake of the explanation back then, but we will not act like this ray just goes straight. It's not really correct. So what we're gonna do one refraction, get this ray. So if we go back to our code right now, we have this get refracted ray. It's gonna get our refracted ray, this one. But then after we did that, we need to do another refract call to get the refraction of this ray over here. So we need to do another bending thing, and it's gonna go like this. So that's the thing we gotta do. We gotta get this ray, and then we use this ray to get the cube map position, because it bends even further. And it's important because without this part of refraction, the only thing you have is like a magnifying glass, and it's not a spherical body, and it's not going to look as correct as it will look like when you do these calculations. This is the full calculation that you need to use. So let's go back here. For now, ignore that there are two of them. We can easily just go back to that and fix it. But for now, let's just try to refract it only once, so it actually acts as a magnifying glass. First, we can go like this. Refracted ray is gonna be get refracted ray. And here we need to send the surface normal that we already have here, and the ray that the incident ray, which is our direction. Okay, and now we have no idea what's going to happen here. So if we do this and then try to get the cube map direction out of this one, we will get something. But it's not the thing you want. And I'm going to normalize it just because it needs to be a normalized direction. And of course, we need to change the mode to 3. And we get something. So we already have, I'm going to zoom in so you can see it. We have something happening right now, but it's not exactly the thing that we should be seeing. It does something. It definitely bends stuff, but it acts weird. So we gotta figure out what to do next. So let's see. I think the formula is the formula lacks some things that we're gonna figure out in just a moment. that I left out on purpose, or actually we can tackle it immediately. With this formula, the formula we have here, we cannot calculate the second refraction. We cannot calculate this one. There is no way we can do that, because right now, if you just call this function the second time, it's just not gonna work, because the surface normal and everything else here is not really correct. And also, like you need to know if this value is positive, then that means that the surface normal and your incident ray are going towards the same direction. And that, if you check the sphere right here, the only way you could get that is when you hit this spot over here. So what we're gonna do to cover this and this scenario, and to be able to call this same function twice, so it works every time independently of which part of the sphere got hit. Is it the entrance or the exit ray? We're gonna do this. We're gonna say if this C1, which is the dot product, if it's larger than 0, or actually let's do this, if it's less than 0, then the first thing we need to do, this C1 value, if it's negative, it's not gonna give us the thing we want. We want this C1 to be a positive number in this case. You'll see in just a moment. If we do this, it already does different things, but it doesn't matter. Now we're super far from the solution still. If it's not the case and they are pointing in the same direction, then we gotta do something about it. If they're pointing in the same direction, that means that you are actually analyzing the exit ray right now. But that also means that the surface normal is not correct, because in that case the surface normal is going to look like this, and we need it to be let me see, like this, basically in this direction, in the opposite direction. So what you need to do, you need to say, well, I want to have normal, the same normal as I have here. It's correct, but in the opposite direction. So flip it. So when we hit that surface down there, it actually acts like diffraction and not something weird. Because if the normal goes the other way, the behavior can be quite, it can get quite messy. Another thing, if you're exiting this glassy ball right now and not entering it, your eta calculation is not correct. It's not correct because here you're saying I'm entering from this first media to the second media. Now we're doing the opposite. We're going from a media, glassy media to air media. So we just gotta flip it. And the easiest way to do that is by saying that eta is equal to 1 divided by eta. So that fixes that part as well. Okay, and right now our sphere is not really, it's not really doing anything realistic here yet. But we're gonna figure out. Now it's just kind of a magnifying glass. And that's pretty much it. So if we go back here, we're gonna do some changes. So there is a problem in our intersect function before we can do more advanced stuff that we need to fix, and that's the fact that here we are hard coding this camera position, and to be able to do the calculations we're gonna be doing now, we need to change that, and we need to pass this origin, the origin of the ray that you're looking from. So basically your eye or whatever origin is, you need to pass it so we don't read it from camera position here. And then you use origin here, and we have it here, and I don't think we have it anywhere else. And of course it's not compiling now because we are not sending the directions. So for the first intersection we're just going to be using the old one, camera position, and now it works like it worked just a second ago. That's the first thing we got to do. The second thing we're going to be lacking when we start doing these calculations is the point where we hit the sphere when we did this ray sphere intersection. So we're going to output that point here as well, so we can use it outside of the function. So we can name it p hit, the same as it was here, like this. And this is not going to compile again because right now we gotta have this p hit defined here, and we need to pass it to this function, so this function has something to put it into. Cool, and now we have the point where we actually hit the sphere. We can now finally proceed. So, after we refracted, we get this ray over here, the one inside of this glassy bowl, right? Now let's do the refraction again. Let's just bounce it back against the back of the sphere out. The way we do it, we need to do intersect again. And this time, instead of having the camera position as the origin, your origin is actually the point where you hit the sphere. Because when you look into this one, you'll figure out that this is your origin now, and it's pointing towards down. So we do p hit, because here in this first intersect, p hit is where we output this point where we intersected with the sphere. So you can use that here directly. Then direction is now the refracted ray, because if you look into this one, this is the refracted ray, this whole thing. So we can use that as a direction. And we'll normalize it, because directions are usually a normalized vector. We need to normalize it. And then we have surface normal. That's gonna be let me see. Yeah, the surface normal, we can use the same variable, because this is just gonna be used by intersect function to put in the new surface normal value there. And then you can type as the last one p hit again, because this is gonna be, now it's gonna use this variable to put the p hit position. Okay, so if we hit this, that means that we managed to hit the back of our sphere, and that means that we want to refract from that point behind the sphere. So we need to do this phase now. So this phase over here, we need to do it now. So we do exactly the same as we did the first time. We say refracted ray. We can reuse the same variable, and we say get refracted ray, like this. But what's our surface normal? Well, it's again surface normal. Why is it again surface normal? Because when we did this intersect, we did the calculate. Now it's a bit messy, I know, but it's basically we hit it there and we got a normal that's like this. So we can pass that normal inside, and now our function knows that we are exiting the sphere, so it's gonna flip the normal so it points in the opposite direction of our incident ray, and it's gonna know what to do, right? And then you do a direction, right? Direction is in this case gonna be refracted ray, because it's our refracted ray is now the incident ray for the second scenario, and we're gonna normalize it. Eesh, now it's already looking better. So let me see how we set these things up. So refracted ray, yeah, and that's pretty much, it gives you something already. And now if you start playing with these numbers, you're gonna be seeing different things. Okay, and it might be that I flipped something. Let me see here. So refracted ray is gonna be this one. Okay, it might be that I flipped these two. No, I did it. Okay. Cool. So it still doesn't look as good as it should look like. I think. Let me see. The thing I want to do, I'm gonna paste a piece of code that I have in from one of the future tutorials that's gonna enable us to rotate our camera around here. Camera zoom. Yeah, we use canvas position now. Sorry, we changed it. Okay, and I also play it with some other things. Okay, one more thing we gotta do is we gotta position our camera a bit differently. Or actually, we can position our sphere a bit differently to make it stick to the center. Let me see where we placed it. Oh, 2.2, yes, it's quite far. So if we place it in the center, it looks like this. And we're gonna make it bigger. Okay, so it took me a while to figure out what's wrong, and it actually was we had C1 here instead of C2. So once I do that, you actually get a sphere that makes sense. And now you can play with this index here to get what you want. And this officially marks the end of this tutorial. In this one, you learned about refractions. So you know how reflections work, you know how refractions work. You know how to draw a sphere in the scene, you know how to draw a cube map around it. You have a pretty big power in your hands right now already. In the next tutorial, we're going to be talking about Fresnel, or the way we can play with refractions in a slightly different way. Also, we're gonna start exploring how we can make the sphere more glossy looking and why it doesn't look glossy at all at this point. So stay tuned, and until the next time, stay safe.